Ladies and gentlemen, the future of electric aviation and personal watercraft. Who knew 3 years ago that that would even be a thing? After developing and commercialising electric VTOL drones for more than a decade, Josh Portlock, the CTO, co-founder of Electro.Aero Proprietary Limited, saw the opportunity to scale up the technology to the manned aviation industry and started Electro.Aero. In 5 years, they have achieved many world firsts in electric mobility, including developing one of the first compact proof of concept personal VTOL aircraft prototypes that they call FlyKart. It employed 8 electric ducted fans to carry a person vertically. Bring it on. They obtained the first CASA light sport accreditation in Australia for the world's first 2-seat electric aircraft at the start of 2018, becoming the first and only company profiting from electric aviation to date. They wrote the SAE International standard for electric aircraft charging and are the first company to develop and sell dedicated electric aircraft chargers compliant to the international standard. Last year, they developed the world's first actively stabilized electric hydrofoil personal watercraft called the Wave Flyer, which quite literally flew over waves. This year, they built and flew the world's first 2-seat electric ducted fan microlight aircraft. In this talk, Josh will share some of the lessons learned from these projects and other contract work undertaken on various electric aircraft projects, including Bell, XTI Aircraft, and NASA, to name a few. He's also taking orders. Ladies and gentlemen, welcome Joshua Portlock, the co-founder of Electro.Aero Proprietary Limited.
Thanks, John. I appreciate that a thorough intro. I wasn't expecting to read the whole thing, but I'll at least not have to repeat any of it. I can get straight into the slides and share my lessons learned. And I think, I'm often presenting to non-electric enthusiast groups. So I usually start with a bunch of why electric, but you guys already know that. So I'll get straight into it. But what I did want to emphasize was the S-curve of adoption and how we're seeing it in the automotive sector. So I like to explain it like a horse race. So like, early on, a decade ago, there was this early adoption of electric vehicles, the Tesla Roadster, and some sort of entry-level ones like the Miev and Leaf. And if you look at the S-curve adoption of projections of when certain countries are going to go 100% electric, you got Norway being the most ambitious early adopter, Netherlands, UK, France, Canada, Germany, and some laggards like China and whatnot that are definitely adopting electric quickly, but they just have such a gargantuous undertaking to change. Australia doesn't even register on here because we haven't set a target for percentage to electric or 100% electric, but it's inevitable. And I think really the 2050 conservative German estimate is my opinion when everything new will be electric. And it's just curious to see the rate at which that adoption happens in automotive. And I sort of joke about the horse race of all the different automakers, jumping on the bandwagon. And before you know it, you got crazy cars like the Cybertruck. Who doesn't want a Cybertruck, right? So if you look at the S-curve adoption for other electrification, going way back from when electric motors were first introduced over 100 years ago, there was a huge uptake. As soon as they stopped having to, run steam engines and they could run electric drives, it was just a phenomenal fast uptake, but it actually has gotten steeper. The funny thing about it is like, you look at the uptake of electric lifts and electric, trains and things like that. It was kind of a gradual S-curve, but things like started to get steeper and steeper and steeper to the point where you've got, internet access and cell phones and more recently car adoption. And the sort of projections for automotive in the medium to high optimistic view is that this red section at the bottom is the sort of medium to optimistic view on electrification for vehicles. And this is actually, to clarify, this is of vehicles on the road. So it's not of new vehicles that's likely to transition to 100% in the next 30 years, but this is of the actual vehicles on the road. So there's a projection somewhere between 20% to over 50% of electric vehicles, of vehicles on the road being electric. And that's somewhat true for watercraft and aircraft too. I want to explain that what we're seeing is just a slight laggard of watercraft and an even longer laggard of aircraft, but they're definitely on that same S-curve trajectory. And we're at the infancy of aviation electrification now, kind of almost too early, you could argue. So hence we're applying our technology to watercraft because it's actually a more viable use case with a likely sooner adoption rate, and automotive is even more advanced than that. And you could argue trains have almost all gone electric and elevators have almost all gone electric. I think you'd be hard pressed to find a steam engine elevator anywhere. So yeah, this is an overview. Hopefully the audio is coming through okay of what we do. John, do you want to confirm that audio is good?
There's no audio, Josh, but I think the message.
Oh, okay. Well, look, the visuals do speak for themselves. Sorry for the lack of audio, but we basically 2.5 years ago, we certified the world's first electric aircraft in Australia. And even to this day, we're the most experienced electric aviators of commercial operated electric vehicles. And then more recently, there was the first flight of the trike you see here taking off. So I don't want to repeat the intro that covers all those world firsts, but really the lessons learned have been that electrification is medium hard in vehicles, harder in watercraft, and extremely hard in aircraft, because energy density is the sort of somewhat limiting factor at the moment, and aircraft are the most energy dense, most demanding, in the sense that you're trying to lift your own power source and you don't have the luxury of a depleting weight of the fuel. So you are carrying the entire battery mass from takeoff to landing. But we are seeing this adoption of electrification, and there's about 3 major verticals that we're focusing on within aviation. You could argue we're focusing on all 3 verticals of air, land, sea, but even within aviation, there's an immediate opportunity in 2-seat recreational fixed-wing aircraft that we're focusing on now. There's a emerging category of 4 to 5-seat fixed-wing air taxis, which we're providing chargers for and batteries and subsystems. And then an inevitable but very sexy eVTOL category where they take off vertically and transition. But from my over a decade experience in electric vertical takeoff and landing drones, I know that it's not only the most, it's actually technically doable already, but it's definitely the most energy intense application of electrification, because you use a huge amount of energy to take off vertically. And then the scariest part is using the same amount of energy to land at the end of the mission. So if you are both vertical takeoff and vertical land, there are some aircraft exploring fixed-wing landing to save on that energy consumption. But that landing is the most energy demanding part. And all of you who probably know batteries quite well, they don't like being thrashed in the last 20 to 30% of their capacity. So you end up you have to leave a huge amount of reserve, 20 to 30% of the battery, in order to land vertically. So you now have this very challenging use case of battery electric aircraft having to take off with a huge amount of power, cruise with a much less power, and then use a huge amount of power again at the end of the mission. So we've got a lot of customers we're selling our technology to in the eVTOL sector, but the reality is it's still 5 to 10 years away from being commercially viable to satisfy the emergency reserves. So because of that, we've sort of dialed back our ambitions on VTOL, said, yes, we're happy to be a supplier to the 275 different electric aircraft projects around the world. Not all of them will be winners, but as long as they're happy to buy our technology and standardize to our charges, and we're at the coalface with them developing the technology, there's still a viable business model in there for us helping them. But we're definitely more focused on the fixed wing 2 to 5-seat market in the shorter term, and even shorter than that in the watercraft. So a quick summary again, we've sort of dabbled with everything from personal drones to fixed wing and eVTOLs. The vehicle in the top right is the Trifan, which is a subscale model. You can see me standing on the right flight testing it in California. And that's a 800-pound, with the old units, it's 300 plus kilos of drone to demonstrate the aerodynamics of this eventual 6-seat personal jet. So that was a lot of fun, and it sort of proved our technology and sort of cut our teeth on some ambitious projects. But we've sort of dialed it back to the going, all right, we're happy to support those industries try to develop technology and commercialize them and certify them, which is the bigger challenge. But really, we've got such great high energy density application technology now, we should look at other applications that need the high energy density. So one opportunity that came up was watercraft. And last year I was asked to work on a watercraft tech demonstrator for the University of Western Australia. And we converted a jet ski to a hydrofoil. And in doing that, we realized there's a 75% technology overlap between aircraft and watercraft, especially hydrofoil watercraft, which are basically just drones on stilts, is the way I explain it, because we have actively stabilized hydrofoils underneath the water, stabilizing the craft, and little ducted electric propulsors, much smaller than the aircraft ones, but still similar fluid dynamic principles, that we're propelling under the water in order to reduce the drag of the hull and get it out of the water. So by thinking differently, how do we solve these electrification problems? There's definitely some great examples of conversion with, what SAE are doing, and other people converting cars is a great use case of the technology. But what we're seeing to really revolutionize aircraft and watercraft, we have to think differently about how they're propelled, not just replacing the engine, because then you're going to have a really slow, heavy boat that doesn't get very far, and no one will be happy with that. By getting up on the hydrofoils, we get 75% less drag. So just to put that into context, that's 4 times more range for the same battery size, or a quarter of the batteries. So think about the cost and weight saving of a quarter of the batteries for a given range, or double the speed is another example. So if you want something fun, a recreational vehicle that's electric, you want to go fast and feel like flying over the water, you want to get up on the hydrofoils. And not that hydrofoil technology is new, but actively stabilized hydrofoils combined with electric propulsion is very novel. And we've been building a strong intellectual portfolio around that actively stabilized electric hydrofoil propulsion, and then offering that to other watercraft. So the medium-term mission of our subsidiary Electro.Nordic is to offer our propulsion systems to other watercraft to help them transition from petrol engine watercraft to hydrofoil electric watercraft. And in doing that, we sort of become the Rotax of electrification, if I want to give an analogy. Rotax, which is a subsidiary of BRP, Bombardier Recreational Products, is one of the leading engine providers for aircraft and watercraft. So they are already in both verticals. They have a 95% market share in 2-seat recreational ultralight aircraft, which is just phenomenal. It's basically a monopoly. And a 60% market share in personal watercraft, so jet skis. So in that regard, if we can be the equivalent of a Rotax to the electrification phase, then we can see the similar success they've had over the last 50 years of being a leader in propulsion for those recreational markets. We'd like to be the equivalent leader in this next wave of disruptive electrification for those two industries. And in doing this, we've built a family of technologies. So it's a product suite of electro management system, as we call it, the electrical safety system that governs all the communication between everything. And that's typically communicating to most things over CAN bus, whether it's to the batteries, to the safety systems, to the auxiliary power systems, the power distribution units and whatnot. Serial to, say, an autopilot, communicating to the speed controllers, communicating to the charger ports, because we already develop and manufacture chargers, so we're very comfortable with communicating to the aviation chargers. And being this central location of technology means we can be sort of the one-stop shop for companies wanting to convert, transition to electric aircraft and watercraft. I don't have time to show the charger, but I'll skip through that. And just emphasize that we've got this roadmap to electrify aviation from light sport, fixed wing air taxis to VTOL air taxis. And the exciting thing to share is we've already started foiling our latest prototype, the Waveflyer. And the Waveflyer sit-down version is a lot of fun. It really feels like a fighter jet over the waves. So thanks for your time. Look forward to answering questions in the panel session at the end. And the future is electric.
Fantastic work, Josh. Nice to see a young man grow a career. Now, I've got the Premier of Tasmania's phone number here for you. We're looking to replace the Spirit of Tasmania's. And who knows, you sound like you'd be the man to give us what we need.
Happy to help.
Yeah, I'll bet. Yes, and a 10% commission, of course, for the introduction.